Please don't forget to like, share and subscribe my YouTube channel. Today we'll see about the Kepler's law of planetary motion. This law has totally 3 laws that just exists by Johannes Kepler. He's a German astronomer. Kepler's first law of planetary motion states that about the law of ellipses or the law of paths. All planets revolve around the sun at one focus. If the first law, all planets move about the sun in an elliptical orbit about at one focus. You see here, the path is elliptical. This is the semi-major axis, and this one is the semi-minor axis. For example, our Earth is just revolving around the sun in an elliptical orbit and has one focus, is this one or at this point. Kepler's second law, planetary motion, the line joining the sun and the planets sweeps out equal areas in equal interval of time. The other form is radius vector joining any planet to the sun sweeps out equal areas in equal time interval. You can see here that the planet is just starting, our Earth is just starting to pass, to follow this path, this elliptical orbit. Now if you just take this path, let's take here, this is one area. If this distance, the one just traveled is delta t1, and if it just moves again another distance a2, if the time interval that takes to travel this one and this one are just the same, then the area travels a1 and a2 are the same. This is Newton's law of gravitation, what it just tells us here. You can see here the planetary orbit. Kepler's third law. Kepler's third law of planetary motion is just the law of periods. The square of the several periods of the planets are directly proportional to the cube of their mean distance from the sun. You can see here, you see, this is R1 for the planet 1 and R2 is for the second planet. They do not take the same time to travel around the sun. They take different times for this purpose. Now let's see this example for that purpose. 2 satellites are in orbit around Mars with the same orbital radius. Satellite 2 has twice the mass of satellite 1. The radial acceleration of satellite 2 has A, twice the magnitude of the radial acceleration of satellite 1. B, the same magnitude as the radial acceleration of satellite 1. C, half the magnitude of the radial acceleration of satellite 1. D, 4 times the magnitude of the radial acceleration of satellite 1. You see, you have 2 satellites. Here is the Mars. 2 satellites are just revolving around Mars. One is at this point and the other is around this path. They just follow this tangential path. Now you can see here that the radial acceleration, this is just the acceleration, centripetal acceleration and radial acceleration are the same quantities. They are always acting towards the center of rotation. And you can see here that if you just take this is just R1 and this is just R2, the same orbital radius. If these are just different, it's possible. But both of them are just following the same path. This one R1 and R1 are just moving. If you just compare here, for R1 and R2, you can take that R2 is greater than R1, and centripetal acceleration is just given by V squared over R, which implies that AC is inversely proportional to R, which means R increase means this implies that AC decreases. But in our case here, the two satellites are just moving in the same path. Both R1 and R2 are the same. R1 is the same as R2. So, since they are just moving in the same orbital path, then the magnitude of the radial acceleration is just AC is proportional to 1 over R1 and AC is proportional to 1 over R2, or you can write here AC R is equal to constant. Since they are just constant, AC1 R1 is equal to AC2 R2. Then you can take here that AC2 over AC1 is equal to R1 over R2. So the path is just R1 is R and R2 is R. This is just 1. What does it mean? AC2 is equal to AC1. So the answer is B. Why? Because the centripetal acceleration is just dependent on the radius and the velocity. Their velocity is equal, and as a result, the radius is just equal. Therefore, the magnitude of the radial acceleration is equal. So the answer is going to B is the answer. Let's take another example of Kepler's law of planetary motion. This question is just based on what is known as Kepler's third law. For any planet, comet, or asteroid orbiting the Sun, Kepler's third law may be written as T squared. This is Kepler's third law, proportional to R cubed. And where T is the orbital period and R is the semi-major axis of the orbit. What is the value of K if T is measured in years and R is measured in astronomical units? One astronomical unit is AU, is the mean distance from the Earth to the Sun. Now you can see here that T squared is equal to KR cubed, which implies that T squared over R cubed is K. Therefore, one can write here that T squared over R cubed is equal to K. To determine K, you can have K is equal to, the time is in years, 1 year, the whole squared, and R cubed is 1 astronomical unit, the whole cubed. This is 1 year squared over astronomical unit cubed. This is the value of K. This is concerning about part A. Use this new value K to quickly find the orbital period of Jupiter if its mean radius from the Sun is 5.2 astronomical unit. Now here you can have that T1 squared over R1 cubed is equal to T2 squared over R2 cubed. This is just the same as the orbital period of, this is just T2. Let's take this T2 as, let T2 is equal to the period 5. R2 is equal to R of Jupiter, and this is 5.2 AU. Therefore, we can take here that T1 squared is the Earth's 1 year squared over R1 is 1 astronomical unit cubed is equal to T2 squared over R2 is 5.2 AU cubed, which implies that T2 squared is equal to AU cubed. This unit is just cancelled, and that is 5.2 year squared. So T2 becomes the square root of 5.2 year squared. All this is just the same as 5.2 under the square root years. This is just the value of Jupiter to move around the sun or to revolve around the sun. This is just, don't forget here that here is just 5.2. This is 5.3, and this is cubed. So this is T2 is equal to 5.2 root 5.2. This is yes. This is the value that we are going to get. This we're using Kepler's third law of planetary motion. This is the period of Jupiter, and when you just simplify this, we can get 11.86 years.